So in the previous class we were looking at the growth of nanowires using the case study. So this was a case study that utilizes eutectic phase diagrams, and this is VLS process, right. So I have a vapor liquid interface, liquid solid interface where silicon starts to precipitate, vapor liquid interface where silicon comes and reacts with the liquid to form more and more silicon gold liquid, and at some point when once it hits the X star, it would along this line it would start precipitating out more and more silicon, right. So and the silicon gets precipitated on the liquid solid interface, and that is why it is called vapor liquid solid reaction or vapor liquid solid process, where two interfaces are important, the vapor liquid interface and liquid solid interface, right. But this can be explained with the help of a eutectic phase diagram, a simple eutectic phase diagram. Okay, so in this class we will look at a couple more phase diagrams, right. So that are useful to explain several other ideas in material science, and so you will see by the end of this class where we are getting at, and these are what are called needle compounds. Phase diagrams of needle compounds, right. And what is a needle compound? A needle compound is something that has very low solubility of two in of one component, right. So it can be 2 or 1 of a component in a particular phase, right. For example, we said something like if I look at gold and silicon, okay, there is a eutectic is fine, but if I actually zoom into this, right. So if I zoom into this and look, there should be some we said this is gold plus silicon, right. But what we actually meant was this is a phase, this is some alpha phase which is rich in gold, almost pure gold, right, with very low, very low impurity of silicon, right. And if I zoom it up, if I put a magnifying glass and zoom it up and then see, so that will look something like this. So that is my alpha phase, right. So it is almost like a needle, right. So it is a needle compound. In phase diagram, right. So if I zoom it up and see here, okay. So essentially a needle compound is something that has very low solubility, right. So of any other so only that composition, for example, only here X2 equal to 0 is the only composition where I can find this this particular phase, right. So similarly I can also find in some other material X2 equal to 0.5, I can find some kind of a needle compound, right. So away from this, right, so away from this 0.5 I will start forming another phase, this side of 0.5 I will start forming another phase, but the phase of interest, POI, not person of interest, phase of interest only happens at a certain composition, right. So and those certain compositions, these phases look like needles, and hence they are called needle compounds, right. Okay, fine. So now let us do a couple of quick problems of so if I look at the delta G or G mix as a function of X2 of the needle compound, right. So needle compound does not really show any solubility of X2, let us say, and so it is going to look like so it is very much rich in 1, and so this is how it is going to look like, right. So a very narrow delta G G mix, okay. So as a function of this is for alpha phase, okay. So and then this is alpha phase or solid phase, okay. And then I am comparing it with a liquid phase. Of course in a liquid phase there can be more solubility, of 2 in of 2, right. So Okay, now let us give an example of this case, right. So this is so in countries, in cold countries, okay. So in cold countries, so once the temperature goes below 0 degrees and there is a snowfall, right. So snow tends to accumulate on roads and other things, right. So this is snow, this is a road, this is a cross section of a road, right. So this is snow, but so it's not very nice that so I have this solid ice on the road. Okay, so what people do is people use what is called an antifreeze, some kind of a salt, right. So weather predicts that so there is going to be snowfall today, right. So the temperature has gone to minus 5 degrees Celsius or minus 10 degrees Celsius, right. I am in a very cold country, so there is going to be snowfall. So when there is already a prediction of snowfall, what people do is people spill this thing called antifreeze on the roads, right. So wherever so what the antifreeze does is antifreeze melts the snow even at minus 5 degrees Celsius or minus 10 degrees Celsius, whatever is the temperature, okay. And if it melts, then I can drive around on the roads, and so it's a much safer thing if the snow melts. If the snow is there, I have the slippery snow, and it's snowfall looks good, right. So it looks very artistic, and you can paint pictures and things like that. But after the snowfall, that is when the hell begins, right. So you have to clean up the snow, you have to shovel the snow, as they call. It's slippery, you can't walk. If you are walking, you are slipping. If you are driving a car, there is not enough traction to the wheels, right. So it's a nightmare, right. So you ideally want to prevent the after effects of snowfall. So what you do is you put this antifreeze thing, and then antifreeze is supposed to help you melt the snow even at low temperatures, even when my temperature is below 0 degrees Celsius, right. Now, can we explain the functionality of this antifreeze from the idea of so delta G's and the phase diagrams, okay. All right, so let us do that. So I am going to say that let us look at okay, so and that is a classic case of this phase diagram, or this G versus X2 that I have drawn, G mix versus X2. Okay, now X2 is the content of antifreeze, 2 is my antifreeze or some salt or something it is, okay, and 1 is my water, right. Now water doesn't mix with antifreeze in the solid state, right. So in the solid phase, right, so if I have, that's the alpha phase, in the alpha phase water hates the antifreeze, okay. So that's my in the alpha phase water hates antifreeze, alpha or solid phase, right. So as a result alpha is a needle compound. There is no solubility of alpha, there is no solubility of antifreeze in water, right. So in the alpha phase, so alpha phase is almost a pure ice phase. You can approximate alpha phase to be a pure ice phase, right. So approximate to a pure ice phase, okay. Whereas the liquid phase has good solubility, okay, of water, of antifreeze in water. So now you can see what we did earlier also, right. So when we are looking at the gold silicon phase diagram, we said, all right, so gold itself is solid, but as I keep on increasing the silicon, I can liquefy it, right. So that's what we are going to do, right. So even with antifreeze, as I keep on increasing the concentration of antifreeze, I am going to liquefy. So antifreeze wants to stay in a liquid state, so it will reduce the melting point low enough that so I am now going to create a liquid of antifreeze and water, rather than a separate solid of antifreeze and solid of solid of ice, okay. So that's what we are going to do, and for that so let us quantify it. So earlier we were just looking at a qualitative picture, this time let us quantify it, okay. All right, so for quantification I am always going to look for equilibrium. equilibria, right? And so again let me go back to solid liquid equilibria now, and I mean this is much more steeper, right? So this is the alpha phase, this is the liquid phase, and I am going to look at solid liquid equilibria, and the solid liquid equilibrium exists at 0 degrees Celsius if there is no antifreeze. Okay. Now I have to depress this melting point. So I am going to look at the melting point of so liquid contaminated with antifreeze. And I want to reduce it. I want to reduce it below my. I want to reduce it. Objective is to reduce it below the ambient temperature. Okay. All right. So equilibria. So how do I solve problems of equilibria? Right. So this is actually going to tell you how to do that versus x2. Right. So this one and this one. This is liquid. This is alpha. Actually, it's much more steeper. Okay. Now I am going to say that so the liquid phase exists in equilibrium with solid phase, and so that means that mu of mu of 2, right? So x2, or I can just say mu of water in the ice phase is equal to mu of water in the liquid phase, right? So this is the condition for equilibrium, right? And we are saying that mu of water in the ice phase is actually mu of water in pure ice, correct? Because ice is not really getting contaminated. So ice is what is it? Is a needle compound, not getting at x2 equal to 0. Alright, okay. So not going to get contaminated with antifreeze. Okay. So if that's the case, then so mu of ice, mu of water in ice, or mu tilde of water in ice equal to mu of water in liquid. Okay. And mu of water in liquid we know, right? So that is equal to mu tilde of water in liquid. This is for pure liquid, no contamination. Now I am contaminating it with a small concentration, right? So at small enough concentrations I can consider that the compositions are the same as activities. So I can just write it as x equal to a, right? So we can assume ideal solutions at small concentrations, right? So if xH2O is small enough, then activity becomes the same as composition. So I can write xH2O equal to AH2O, right? That's what is called Raoult's law. I didn't discuss it, but you can just assume that that's the case. Okay. All right. So now what I have is so since xH2O at dilute solutions this is still valid, right? So this is concentrated xH2O, but at in dilute solution limits xH2O equal to H2O. This is a valid relation, okay? But xH2O itself is equal to 1 minus x2, right? x2 being my antifreeze, and so I am going to write this as mu of ice in water, mu of water in ice equal to mu tilde of water in liquid plus kBT times ln 1 minus x2, and x2 is small, so I can just approximate ln 1 minus x2 to be equal to minus x2. Okay. So mu of H2O in ice, right, equal to mu of H2O in liquid, right, minus kBT x2. Okay. So this is how it is going to come out as, all right. So now mu of liquid water pure minus mu of water in ice, Now that is nothing but that is my latent heat of so I mean that is just delta S times T, but delta S at of the pure melt, right, times T minus T pure melt. So this I can get from just a Taylor expansion, right. So I mean delta mu is equal to d delta delta mu by delta dou T times delta T, right. So that is the Taylor expansion that I did at a given temperature, right. So and then this turns out to be the entropy, right, at the T pure melt temperature, at the melting point of the pure compound, times delta T. Delta T is T that I am at minus T pure melt. Okay. So this is just a simple Taylor expansion. All right. Okay. So this sort of problems we did earlier, so I am not going to go into details, right. So I am not going to derive it with so much rigor, right. So just you can, if you do not understand this, try deriving it. It is just a simple Taylor expansion, right. So I am not writing the first term, which is mu of solid minus mu of liquid at T melt, and that is equal to 0, right. So because mu of solid equal to mu pure of liquid at the melting point, right. So that is a 0 term which I have not written deliberately because I wanted you to figure out, and the second term is d delta mu by dt at T pure melt times delta T, right. So that is the one that survives. Okay. All right. So now what I have then is kBT x2 is equal to delta S of pure melt. This is delta S at the melting point of water, which is 0 degrees Celsius, T minus T pure melt. Okay. No, I think the sign will change. So we can actually check what it is exactly. But the sign is going to change, T pure melt minus T, right. So this is going to be a positive quantity. So I will right. I want this Tm to be the melting point, right. So I have depressed the melting point in some sense, right. So I can actually write T pure melt, which is for the pure compound, minus T melt is equal to kBT x2 divided by delta S of the pure melt, right. So I am actually depressing the melting point by this much, right. So or I can actually calculate the T melting point is equal to T pure melt divided by xB divided by delta S, actually kB x2 divided by delta x plus 1, right, and delta S for water to ice or ice to water is typically about 2.65 kb, right. So these are numbers, this is called Troughton rule, but based on that I can just say that pure melt or Richard's rule, I forget which one it is, divided by, I can put a number to this, by 2.65 plus 1, right. So if my ambient temperature is minus 10 degrees Celsius, I need to use so much of antifreeze, right. So xB is my antifreeze composition, that this number becomes T melt, right. So that is the idea, right. So T melt should be slightly less than T ambient, right. So I should increase the concentration of xB should be increased such that T melt is slightly less than T ambient, and then I can liquefy the snow. Okay. And this is not going to work forever, right. So I can't go for xB equal to 1, xB should be still dilute concentrations, right. So relatively if I have a snowfall at minus 5 degrees Celsius, minus 10 degrees Celsius, right, so I can use antifreeze, right. if I have a snowfall at minus 50 degrees Celsius, then I really cannot melt off all the Himalayas with antifreeze, right. So, for example, okay. So, first of all, I do not have so much antifreeze. Even if I have so much antifreeze, so that's not possible, right. So, this works in the dilute experiments, okay. So this I am just thermodynamically explaining that I can reduce the melting point, right. So, which is what we have already seen, right. So, by contaminating the liquid phase with more and more in this case the antifreeze, in case of gold with more and more silicon, right. I can there I have precipitated out silicon, but here I am precipitating out the water, right. So, I want to melt off the ice, right. So, I want to melt off the ice and let it go down the drain, right. So, I can do that with a bit of antifreeze. The idea that I have used here is ice in the ice phase cannot take any antifreeze. So, when I put more and more antifreeze, it is like increasing the temperature, right. So, it goes in this direction and it starts to liquefy. Okay. Now, how much antifreeze can I put is just a phase equilibrium thing, right. So, we just calculated by equating the mu's, right. So, the mu of the solid should be equal to mu of the liquid, but solid is almost pure solid. So, I will take the mu tilde of the solid or mu pure of the solid. Liquid is not pure, but it is dilute enough that I am going to assume that mu equal to mu tilde plus 1 plus kBT ln x H2O, right. So, that's the approximation that I did. Okay, that is so here this is one case study where limit where needle compound exists at x2 equal to 0. X2 equal to 0 means impurity is equal to 0. So, the exists in the solid phase, right. So, in alpha phase, right. So, now let us look at the other limit where the needle compound exists at x2 equal to 1. Okay. Now, here is an interesting scenario, right. So, what is the case that I am going to discuss, right. So, now here I am going to say that okay, I have a phase here, right. So, this is x2 equal to 1, this is a needle compound, right. This is G mix again, this is x2, right, and I have another phase where I have slightly more solubility of 2 in this is the alpha phase and this is the needle phase, right. So, let us just call it that, okay, or beta phase. Beta is the needle phase. Okay. Now, the problem that I am going to discuss here, case study, is how can I get vacancies in a solid? Right. Thermodynamic vacancies, what are called thermodynamic vacancies. Now, you can always imagine that every solid, right. So, I take a pure solid, right. So, a Kossel crystal, there are some atoms, right, at any given temperature, right. So, I will always find that there is some of these atoms are missing, right. So, it is not a perfect Kossel crystal, there are some atoms which are missing, right. So, this is a vacancy. Okay. I am going to call this vacancy, let us give it a name, I am going to call it a Vacadium atom, just like uranium, plutonium, etc. I am just going to call it a Vacadium atom, and I am going to look at this problem as my species 1 plus Vacadium, species 1 can be platinum, whatever. So, pure metal, one of the pure metals, right, Vacadium solution, right. So, I am going to look at the solution of species 1 and Vacadium, right. So, so Vacadium is like my species 2, right. So, I am going to look at the solution of species 1 with Vacadium, and species 1 can be platinum, it can be palladium or something like that, right. So, typically what happens is so when I put platinum, right, in contact with vacuum, now vacuum is full of Vacadium, vacuum is essentially nothing and Vacadium is also nothing. So, I can consider vacuum as an FCC lattice or some Kossel crystal lattice of just Vacadium atoms. Does not matter what lattice it is, you define what lattice it is, but whatever the lattice you give it to the vacuum, right. So that is full of Vacadium atoms, right. So I am going to play with your minds now and then say, oh, vacuum is actually something, right. So all the philosophers say the opposite, right. So, oh, this is just material, it's essentially nothing, but I am saying I am putting a material in nothing, right. And I am calling it Vacadium. Okay. So anyway, so this is just for fun, so don't take me too seriously there. So I'm so if platinum is in a combination with a Vacadium, right. So that is, or so a vacuum, that's the source of vacancies, which means platinum can go out into the vacuum and then a vacancy can come in, right. So that's how I put in vacancies into my system, right. Now I want to calculate how many vacancies am I putting into my system, okay, and that I am going to do it in the formulation of a needle compound, okay. So the question that I am asking, how many vacancies or the concentration of vacancies that exist in my material at a given temperature. Okay. Now, all right. So I have, so I am going to look at this in terms of needle phase diagram. So I have an alpha phase is FCC platinum, let us say. This is alpha is FCC platinum, okay. And then I have a beta phase, and this beta phase, right, and beta phase is a vacancy rich phase, or a lattice of Vacadia, right. It can be vacuum, right. So which is a lattice of Vacadia, okay. So that is the beta phase, right. So it is difficult to put so many platinum in the vacuum, right. So if alpha phase is platinum and beta it's in vacuum, it is so some platinum can go, but so since this is vacuum, I can't really put a lot of platinum in it, right. So I am restricted by the partial pressure of platinum that I can put, essentially, right. So vacuum hence is a needle compound, right, which is rich in X2 being 2 being the Vacadium, okay. Now I am going to do a phase coexistence here. I am going to look at the equilibria here. So now alpha is in equilibrium with the vacancy rich phase, which is the beta phase, right. So the Vacadium rich phase, which is the beta phase, right. So I am going to do just an equilibria to see how many vacancies can be there in alpha. I am going to ask the question, at a given temperature, how many vacancies can be there in alpha phase, okay. That is the problem I am going to solve. Now, all right, so this is almost, let me just draw it properly, right. So this is almost, oops, this is, or let me change the color, right. So that way, almost a needle, I mean it's needle in the phase diagram, but these G's also look very narrow, right. So this is G mix as a function of X2, okay. So this is alpha, this is the beta is the vacancy rich phase, okay. So now mu of Vacadium in beta, right, should be equal to, I do this common tangent construction, and I am going to say mu of Vacadium in alpha, right. But again the same arguments as earlier, mu of Vacadium in beta is nothing but mu of Vacadium in pure beta, or the phase where lattice is completely consisting of vacancies, no platinum at all, right. So it is no platinum, right. So that is the pure vacancy phase, or Vacadium phase, right. So since it's a needle compound, even if I have platinum, it will be very low concentration, right. So I am going to approximate mu Vacadium in beta as mu vacancy of pure beta. Okay. All right. Now what is mu vacancy in alpha? Equal to mu vacancy in pure alpha, right, and that's something interesting, plus kBT ln xv or x vacancies, right, and let us assume that alpha is some kind of a regular solution. Why? I mean, so for example, alpha is a causal crystal of platinum, let us say platinum. Why is alpha a regular solution, not an ideal solution, right? So typically I have platinum everywhere. So my AA bond strength is platinum bonds, right. Now platinum has some negative energy, has some bond energy delta E, right. So if I look at that Lennard-Jones potential, when platinum bonds to platinum, I have some kind of a delta E, right. So that's the bond energy, right. But instead of platinum, let us say I put a vacancy here, right. Then I have AB, right, which is not really, I mean, so platinum is bonding to nothing, right. So that's a different delta E AA or EAA, and so this is essentially 0. EAB is very different from EAA, right. So as a result, so I cannot model this with ideal solution, or in other words, so when I am putting vacancy here, I am not interacting platinum with anything, right. So there is no interaction. So platinum with nothing, no interaction, right. So cannot model this with ideal solution, because EAA is not equal to EAB or EAA plus EBB by 2, right. So rather we have EAB, which is different and probably smaller than EAA in this case, right. So this is 0, this is some finite value, right. So the other solution model I know is a regular solution model, where I have an interaction parameter omega, and I am going to model this as an interaction problem, right. So interaction parameter omega with the interaction parameter omega. Okay. All right. So now let us go back. So I just said beta, in beta phase we have absolutely no problem. Beta is the vacancy rich phase, is equal to mu, sorry, let me write the tilde here, vacancy, this is fine. But in the alpha phase, I am going to assume alpha phase to be a regular solution, right, plus kBT ln xv plus omega 1 minus xv whole square, right. So this is how a regular solution, so the activity splits up, right, into kBT ln xv plus omega x1, right, so x1 square, that is 1 minus x2 whole square. All right. Now what does mu vacancy in beta mean? It means to the lattice of pure vacancies, right, I am adding another vacancy or Vacadium, right. Essentially I am doing nothing. So mu beta is equal to 0, right. Similarly mu alpha is a different structure. I am assuming now that all this nothing is existing in a different structure, right. I have a lattice, I can define a lattice is an arbitrary construct, and I am putting instead of putting beta in a causal crystal or a simple cubic, I am putting the lattice of a FCC, and putting vacancies on the FCC lattice, on all sides of the FCC lattice, right. So essentially lattice is a construct and I am putting nothing on the lattice, right, and I have to add nothing to nothing, so that is also 0. Okay, so there is no energy that I am expending in adding nothing to nothing. Okay, so in that case, so this is 0, right, and then I am going to say that mu v beta equal to mu v alpha, and that means that kBt ln xv is equal to minus omega 1 minus xv whole square, right. All right, now comes the fun, right. So, let me rewrite it kBt, this equation, let us call it equation 1. Okay. So, if I am writing equation 1 again, kBt ln xv is equal to minus omega times 1 minus xv whole square. Now, I am going to say, I am going to use this fact that xv is also dilute enough. I am not going to put 50% of the lattice with vacancies, then I do not have a lattice, right. Maybe less than 1%, right, or so vacancy concentrations are typically very small, right. So, I am going to use that fact and then say that kBt ln xv is equal to, I am just going to approximate this to be 1. They are very small compared to 1, right. So, when I say small, it means different things in different contexts, right. So, this is small compared to 1, right. So, this is some number like 0.1% or something, right. Now, 0.1% is very small. So, 0.1 by 100 is very small compared to 1, okay. So, that is that is all right, okay. So, that is equal to minus omega, okay. Now, so what does this mean? Xv is equal to e power minus omega by kBt, okay. So, I have derived an expression for vacancy concentration in a pure compound in an alpha phase, right, and these vacancies are just driven by temperature, right, nothing else, okay. And so it goes as exponential minus omega by kBt, where omega is my interaction parameter, right. In other words, omega tells me the difference between EAA minus EAB or EA or the other way around, okay. And this so so this is equivalent to I have a platinum bond and I have nothing. So, I have broken the platinum bond and replaced it with vacancy, right. So, this omega is nothing but it is a vacancy formation energy, right. So, to form the vacancy I have to break the bond, right. So, I have a platinum bond. If I want to put a vacancy here, I have to break this bond, I have to break this bond, right. So, that tells me what is the vacancy formation energy, and I think you can actually show that omega is nothing but EV, right. So, it is a vacancy formation energy of EF, let us call it EF of the vacancy, okay. So, as a result now xv then becomes exponential minus instead of EF I will just call it FV, not EFV, right. So, minus FV, which is the formation energy of the vacancy by kBt, okay. And this sort of relation, right. So, I always have some finite amount of vacancies in my material, and I have derived it by doing this creative thing of looking at vacancies as some needle compounds, right. And I am going to say that xv is given by this law, and this rule is what is called Arrhenius equation. These sort of equations, right. So, where vacancies, number of vacancies in my material or concentration of vacancies in my material is proportional to or is exponentially dependent on an activation function, and this activation barrier is the vacancy formation energy. If vacancy formation energy is large, I have less number of vacancies. If vacancy formation energy is small, I have more number of vacancies, right. And if temperature is large, I have large number of vacancies. If temperature is small, I have small number of vacancies, okay. Now, typical values of FV, right. So, let us say FV is about 0.3 V or something like that, right, and at room temperature kBt is 0.025 eV, or for sake of convenience I am going to take it as 0.25 eV, right. So, then xv is equal to exponential of minus 0.25 by 0.025, right. This is at room temperature, okay, and that is equal to exponential of minus 10, right. So 4.5 times 10 power minus 5, okay. That is the concentration of vacancies. They are so small, but they still exist, right. Now, I can also so this is very small, but they exist, right. So for every one atom I have 4.5 times 10 power minus 5 vacancies, and these are just thermodynamic vacancies derived from the Arrhenius equation. Okay. Now I want to give this in a unit of per centimeter cube, right. So many vacancies per centimeter cube. Okay. So do this as a just solve this problem as an assignment problem. In the next class we will look at these numbers, right. So I want to look at the number of vacancies per centimeter cube. So far I said there are 10 power minus 5 vacancies per one atom, right. Now the question is, in 1 centimeter cube can you estimate how many atoms are there? Assuming any typical material, let us say platinum, right. So in 1 centimeter cube how many atoms are there, and so as a result how many vacancies are there, right. So in that, okay. So let us do that discussion in the next class, okay. So we can count the number of vacancies. These are thermodynamic vacancies, right. So just by okay, we will start here. I mean, there is no way to see what you have done, so I will just trust you that you have actually done this calculation, but we will start here in the next class, okay. So and then we will say that we will count the number of thermodynamic vacancies, okay. And so the interesting point is, okay, so we came from just creative way of analyzing this vacancy problem as some kind of a phase diagram problem, or so where I have needle phases that are formed, these and needle compound at x2 equal to 0, x2 equal to 1, right. So that is my vacancy rich phase, and I have put my alpha phase in equilibrium with the vacancy rich phase, and then I have calculated the number of vacancies, right. So thermodynamic vacancies, and these just exist at any temperature. Right. So at any temperature everything is facing some kind of vacuum or gas, right. So I will have vacancies, and these vacancies are just thermodynamically determined, right. So just because this material should be in equilibrium with its environment, and environment has a lot of nothing, right. So environment has a lot of nothing, and this nothing actually goes into your material, okay. And so it's a very beautiful way of solving the number of vacancies in my material, and so conversely at any given temperature I will always find defects, and these are just thermodynamically driven, and the most nicest defects are vacancies, or so the most common defects are vacancies. So some sites that are supposed to exist just don't exist, okay, and this is true for any material, right. So at any material you put it at a finite temperature and tell me that that is pure material, that every lattice site is occupied by some atom, I will and show me that, then so I will give you a lot of money, right. So there are always vacancies, and these vacancies if they are just purely thermodynamic, they can come from this nice Arrhenius law that we just derived, okay. In the next class we will look at again a couple more or one or two more case studies from arising out of needle compounds, and then we will start the idea of what is called reaction thermodynamics. So thermodynamics, one is phase diagrams, one leg of thermodynamics is phase diagrams. If I understand phase diagrams, I can construct a lot of these processes as I'm showing you, and the other thing is, in the process itself there are the silicon hydride, or has split up into silicon and hydrogen, so we have to understand reactions, right. So everything needs to be understood from the framework of reactions, right. So alpha gives rise to beta is also a reaction, by the way, right. So liquid gives rise to alpha plus beta, that's also a reaction, okay. So if we understand these reactions, then we can understand phase transitions, and everything in crystal growth is all about phase transitions. How am I transforming vapor phase to solid phase, how am I transforming plasma phase to solid phase, and so on and so forth, okay. So we will do that. So we will look at reaction thermodynamics, and then develop ourselves the language of reaction thermodynamics, and then move on to surfaces and other things. Okay, so that will be the last part of what is called bulk thermodynamics. Okay, so we will start that in the next class after looking at a few one or two more case studies about the needle compounds, right. So something that is useful, right. So how are these needle compounds useful in real electronic devices, right. So those are the things that we will look at. Okay, all right. So with that I conclude it here in this class, and then I will see you again in the next class. All right, thank you very much.